I should say that a lot of what I'd like to talk about is a challenging proposal to you of what autonomous vehicles look like in the next 10 and 20 years. Today, we have 18 Tesla vehicles and other vehicles as well, but Tesla is really pushing the autonomous capabilities, and we're understanding and studying their driving behavior, the use of real autonomy on the roads today, traveling 60, 70 miles an hour, the reality of autonomous driving. So I'm a robotics nerd, a computer vision nerd. I love the challenges, the fascinating questions that deep learning, machine learning presents. When you transfer those questions and those approaches into the reality where human life at stake, what does that look like? There's open questions there, and I would like to argue that full autonomy is farther away than we might imagine. And in order to take the transition to full autonomy successful, both for the artificial intelligence nerds like me and for my mom, who doesn't even know what the heck artificial intelligence is and just wants a car to get her safely from point A to point B, we're going to have to approach the problem slightly differently. So, okay, yeah. There we go. A lot to talk about, but I'll focus on a few key aspects. And I think there is a lot of smart folks here today to talk about various aspects of machine learning applications to autonomous driving and beyond autonomous driving in general, connected vehicles, ethics, and traffic, all of these aspects. So on the deep learning side, I'd like to mention that I just finished teaching a class on deep learning for self-driving cars. My name is Lex Fridman. I'm from MIT. I forgot to mention this part. And I've also volunteered to be the MC for today's event. For a socially introverted nerd like me, this is one of the biggest challenges of my life. So, so the class was, it's available online with all the lectures available there, and they're exploring one by one the different applications of machine learning and computer vision into the autonomous vehicle space, using self-driving cars as a way to teach various methods of machine learning. There was 250 students registered for the course, and over 10,000 students registered online at this point. It was open to the public, and 6,000 of them completed the assignments. And there's been 20, I'll mention the competitions, the deep reinforcement learning and the end-to-end driving competitions that we had. There's been over 20,000 submissions. In fact, the two competitions I'll mention, while if you find this talk boring, you can actually run the algorithms on your phone while you listen. You can train your own neural network on your phone. So I think one thing, because I mentioned the class, one thing that should be described, and I'm not sure how familiar everyone is with neural networks. Sometimes there's an assumption. Neural networks are fundamentally powerful mechanisms of learning, of machines learning. And with the hype that is on deep learning, sometimes we forget to really look at the fundamentals. One of the things I'd like to say is there needs to be, outside of the application development, there needs to be some breakthroughs in deep learning on the academic side, on the research side, because the fundamental unit of computation in a neural network is a neuron. Very simple. Everything we talk about today has this at the core. There's some inputs with some weights on the inputs, with a bias and an output. And there's some weights controlling the behavior of which of the signals on the input come out. So this neuron gets excited when it sees certain things and gets bored when it sees other things. And we need to we need to adjust those weights in an automated way in order to make it produce what we would like, get excited at the right things. Every single thing in deep learning that we talk about has this at the core, and every single method of optimization that is used to train these algorithms trains the weights, adjusts the weights in a very simplistic way on those neurons. There we go. And the basic learning unit, the neural network, is connecting several of those neurons together. This thing is amazing. It's mysterious. We don't understand how it works. All we know is that it's amazing. All the cat and dog detection that you see, that's not as interesting as the power of this, the power of this tool. It's even at the smallest scale of having a single layer. It has the feature, the characteristic of being universal. It can approximate any function. Any function. This feels like an infomercial, but there's a neural network out there that can safely drive all of us home across the country, wherever you came from today. There's a neural network out there that exists that can do that. That should be, if you're thinking about the space where the neural networks sit, there's a neural network out there with a single hidden layer that can do anything you want. Okay, so we need to find that neural network. That's what this is about. But the power of these tools is there. Just make sure I'm on time. Okay. And on what kind of learning problems we have. How do these things learn? On the output, these neural networks produce an output, and if that output does not match what we would like it to produce, the weights are adjusted. What we would like it to produce part is the hardest part of machine learning, because that's the only successes we currently have comes from human beings stepping in and saying what we would like it to produce part. That's supervised learning, saying, here's the output that we need these neural networks to produce. These are basic things, but ones that we really need to understand in order to see where in 5 and 10 years machine learning can be in terms of driving you home safely. The kind of learning we currently have is supervised, augmented, supervised, and semi-supervised learning. What's shown here on the left is who is doing the hard work of providing the right answers. Is it the human or the machine? Human in blue, machine in red. Reinforcement learning, as already mentioned, and we'll mention in the next talk, is the role of the human becomes less and less. You only need to say the right answer in a small, sparse set of cases. And the holy grail is unsupervised learning, when the human has minimal or no involvement in the annotation process. And the kind of neural networks I'll talk about today, and you hear about throughout today, they all boil down to that single neuron. There's nothing special. The rest of it is just fun tricks. These are tricks that make the neural networks learn faster and not get lost in learning things you don't care about. Convolutional neural networks take advantage, they detect, they memorize patterns in space. Meaning if you see a cat in the top left corner of your image, it's the same cat as if it was in the bottom right corner of the image. There's a spatial consistency there that doesn't need to be learned. The cat looks the same no matter where in the image it is. That's a trick that makes it a more efficient learner for spatial data. Recurrent neural networks has a trick for temporal data. If the word cat is in the beginning of the sentence and at the end of the sentence, it has the same structure. Sometimes it has a slightly different context. But the kind of mechanism for learning the patterns, the temporal patterns of that in natural language, that information, is the same. And so it's an efficient learner for sequences, for time sequence data. But it's the same operation. Okay, so what can we use these tools for? As Pratik already mentioned, end-to-end driving. Like I said, if you're bored, cars.mit.edu. You can train it on your phone, as long as you have a Chrome browser. Have not tested on the iPhone. The input is a sequence of images coming from the forward camera, just as Pratik showed. And the output is the steering, acceleration, and braking commands that control the vehicle. Now, this is something I'll talk about at the end in a few minutes, is where does this data come from? This is one of the big challenges. First, it's fundamental breakthroughs in how neural networks work, is my argument. And the second is data. And this particular data comes from a Tesla vehicle when it's driving itself using the Autopilot feature. So the ground truth for steering commands here are coming from either Mobileye or the Tesla data technology. So we're learning, in this case, from another machine. We have a neural network learning from another. We don't know the approaches used in Mobileye or Tesla, but perhaps neural networks. But the point is that we have hundreds of thousands of miles of data here that we can learn from. That's the real world example. And I should mention, having worked with Udacity on their excellent approach to this problem, is the capturing the temporal dynamics of the data. So using either recurrent neural networks or what are called 3D convolutional neural networks that capture the patterns in time is what is most successful for the end-to-end learning task. Lots of fun stuff there. I'll skip over it. Deep traffic. This is the other side, the non-real world data. This is the simulation side. If you simplify the driving task into switch to the left lane, switch to the right lane, accelerate, decelerate, simplify it to just 5 actions, and you have clearly defined lanes, and what a collision looks like is clearly defined, and you have this toy example of the world. You can train a deep reinforcement learning model or any reinforcement learning model that is an input there at the bottom, takes the state of the world, all the cars, their positions, their speed, puts it into a neural network, and as an output produces the value of taking one of the 5 actions: left, right, accelerate, decelerate. Again, trainable in your browser to teach your car to break the law by speeding. One of the interesting things I should mention, as I mentioned, 20,000 submissions already to this competition. Inside MIT, the competitors were only able to achieve 74 miles an hour, and currently the best is 76.29 miles an hour. I encourage you to try to beat it. You get a free shirt. Okay. So my research is in deep learning, but I think in the 20-minute constraint, I think what I'd like to ask is the question that's beyond just the methods themselves. You can read the CVPR and the NIPS papers for that. I'd like to ask the open question of how difficult is driving? What can we learn about driving? How difficult is the task? And which aspect can and cannot be learned? So what does an intelligent, artificial intelligence system look like? There's at the top the world. There's sensors that take in that world, form a representation of that world, learn something about that representation, convert that into knowledge, then use reasoning, whatever the heck that is, that's the open question, reasoning and planning. So using reasoning to build your understanding of the way that world works, and use planning to generate trajectories or actions through that world to successfully achieve a goal. And then finally, the actual physical effectors that realize the plan that you've created. So this is the question. On the left is a human soccer player, and on the right is a artificially intelligent soccer player operating in a similar environment. I'll give him a chance. He deserves it, or she. So the question, I'll mention it in various forms today, is driving. When we first, in the 60s, the artificial community was excited about the possibility of machines. Was excited about the possibility of intelligent machines. They thought the intellectual, quote unquote, tasks were the ones that are challenging. Chess being, or logic problems, or theorem proving being a formulation of the hard tasks. But I would like to propose that currently we see driving as chess. That it's possible driving is much more like the thing that we take for granted, like walking, like natural language conversation. When you wake up in the morning, the common sense things that allow you to navigate throughout the physical space, to have a chat with your girlfriend, boyfriend, wife, or husband, have an argument, as I'll show, as applies to driving. So that's the open question. In this construct of an artificial intelligence system, is driving closer to the formal tasks or to the human tasks? The things, the awareness of self, these mysterious, beautiful things they write poetry about. Imagination, morality, ethics, subjective experience, and high-level reasoning and consciousness. Sensors, all right, we don't have time for all that fun stuff. Forming representation, this is what neural networks are really good at. Before neural networks, we had to do that the feature extraction was done by experts. The actual learning, the reasoning part, let me mention this. And so if you allow me, so I am the MC, so I can do whatever the heck I want, right? No, but if you allow me, I'll take a little more time because Pratik actually ended early. So I have a good full watch on the time. Because we're talking about ducks here, so let's take a minute. No, if you think about the machine learning task that takes the input, the representation of the world, and takes as an output some kind of actionable knowledge about that world, you could think of the image recognition problem that Pratik mentioned, that you could take an image of a duck and it says, well, that's a duck with 98.73%. Then you could take the audio recognition challenge. I don't know is there any way to play that by clicking it? I don't know how that works. You need to click it somehow. Whatever. It sounds like a duck. Don't make me quack. All right. Is that going to work? It's the only audio I have in this entire presentation. Press play. Nope. Well, you know what a quack sounds like. It's not. This is not essential. And the audio recognition problem that takes the audio sample in produces a quack. And then you could take video recognition, the action recognition task that I do a lot of work on. It says it swims like a duck. You can predict that. Yes, success. So the point is, we don't have any mechanisms now outside we don't have a way to learn arbitrary representations of knowledge that build on themselves, which we call reasoning. We don't actually even understand what reasoning is. How do you make neural networks reason about something? This is something perhaps with some beers or whatever we can chat about later. But this is an open question of how, and I challenge you to think that this is the problem that needs to be solved for driving. We need to be able to make neural networks reason. Okay? Planning, the control problem, trajectory, well understood, well studied problem. In the learning domain, reinforcement learning is a method for doing that. Okay, so how much can it be learned? Yes, we can learn with deep learning the representation, the feature extraction step. This is the exciting, big step for neural networks. This is the difference between neural networks and the classical machine learning methods, is that you can take raw data and learn arbitrary representations of that data that are useful for the prediction task. This is the big breakthrough right here, that red box. The fact that that box expanded to the feature extraction. We are now automatically able to learn the feature representation space, the way for extracting that features. But the question is, can we make neural networks reason? Can we make them as part of the learning step plan as they reason. And of course, the end-to-end task of actually going straight from the sensors to the effectors. Put another way, the question is driving closer to chess or the simple deep traffic formulation of the problem, left lane, right lane, accelerate, decelerate, or is it like human conversation, everyday conversation, where there's very subtle, complex human interaction going on all the time that we take for granted? How much of the problem on the right can be formalized? How much can it be learned? How many edge cases are in that problem? Because currently, the supervised learning approach is essentially an edge case discovery process. And finally, the argument I'd like to make, on the left, the semi-autonomous, on the right, the fully autonomous. Semi-autonomous, for those of you that know these, the numbering and the lettering, is the L2, the L3, where the vehicle has control part of the time and is able to transfer that control to the human being. On the right, fully autonomous, when the vehicle has most of the time is able to maintain control, or all of the time is able to maintain control of the vehicle. What I would like to argue in blue is the easier thing to solve, and the red is the harder thing to solve. If we focus on the semi-autonomous vehicles, the Tesla, the current Tesla approach, the L2 vehicles, where the human being gets to deal with the edge cases, the difficult situations, and the machine takes care of the boring bits that it can solve with 99.9999% accuracy. Then the only thing we have to solve, and we have a few speakers here talking about the human factor. We have to solve the human factor. Very difficult problem. The detecting driver state, communicating with the driver, but it's nevertheless an achievable problem. If we go into the fully autonomous mode, then we have to solve all of those other problems. The localization and mapping, scene understanding, movement planning, and the communication with the external world. And this is something that we talk about in the robotics community, obviously talk about a lot, and in the course that I mentioned. But the key to all of this is data. And just to wrap up in a minute or two here, the data is the thing that makes all of these algorithms work. And what I believe, and there's simulation is an exciting possibility, and we'll have someone to talk about simulation today, but right now simulation is not able to represent the real world to the degree that is able to train and do transfer learning into the real world operation of a vehicle. So what do? All right, MIT, what's the best idea around the table? Well, we can get 20 or 30 Teslas and study them. We did just that. Didn't purchase them. Recruit people that own Teslas and instrument the heck out of them. These are $100,000, $120,000 vehicles. We put cameras throughout them, are collecting data every day. They're driving throughout the country today, and we're collecting every single video frame of their movement. What we don't understand is the operation of the semi-autonomous vehicle. Instrumented these vehicles, we now have 1.6 billion video frames. Autopilot is 20% of that. That's a billion. For an academic, it's a terrifying number. It should be terrifying. I came from Google. It should be terrifying for Google as well. That scale of machine learning is one of the big open challenges. What do you do with 1.6 and quickly getting to be 2 and 3 billion video frames? Okay, we can just skip that. This is what the data looks like. This is one road trips, and there's dozens of those happening every month. This is a road trip from Boston to Florida. Human behavior is the thing. Is a good thing to fly through because we have a couple of very smart speakers to talk about today. But throughout all of that data is we're detecting where the driver is looking, gaze classification, CVPR paper, driver frustration. We have a speaker speaking about that. Cognitive load detection, using blink dynamics and the movement of the pupil to detect with neural networks where the how deep in thought the driver is. Okay. There is somebody today to talk about ethics. I'd like to present, this is the kind of thing I think about. These are crowded New York City streets. The question of how to design an algorithm that's able to successfully navigate through this environment. To have a network that's, or a car that's both safe and aggressive enough to make its way through the assertive world of a New York City intersection. So for example, shown here is a car in white pushing its way through, there you go. That kind of assertiveness is currently not available in any, these are things that you take for granted perhaps, but it's currently not available in any autonomous vehicles out today, or not even often a part of the discussion. How do you put assertiveness into a neural network? And in case this is not shown today, I'll end with this. Oh, is there any way you can click on that? Okay, it's the Coach Racer game from OpenAI where they trained a reinforcement learning agent that moves the boat in a way that maximizes its reward function. Well, you would think the reward is finishing the race as quickly as possible, but what the reinforcement learning agent learns is that it doesn't have to finish the race. Very philosophical. It can actually just keep picking up those green little things and racking up the reward. So this is the open question. When you think of designing an autonomous vehicle that navigates safely through that New York intersection, how do you design a utility function, a objective function, a cost function that successfully trains a network that's both safe and is able to provide an enjoyable experience to everyone around it? So here, the boat just ends up going in a circle over and over indefinitely, crashing into the wall and everything. So I would like to argue, be the devil's advocate, I guess, that driving is more like natural language versus something that can be cleanly formalized. Okay, and with that, we have a couple minutes for questions.